let's tackle a step question. First, a little bit about step, which you probably already know, to be fair. Step is hard. Step is very hard. I know people that have done extremely well at maths at Cambridge, and they say STEM is a nightmare. They struggle to do well on STEP. I think the fact that STEP is very hard, I know this is easy for me to say in retrospect, it shouldn't be off-putting. It's meant to be hard. It's designed to be hard. Doing well in STEP compared to other people, of course, is hard. The standard of math applicants is very high, but we don't necessarily need to be acing STEP in order to achieve that, right? A-level for further maths, you need to be at the top of your game to get an A star. You need to be doing well, but at the end of the day, hey, you walk into an A-level further maths exam, you pretty much know roughly what you're going to expect. There's going to be some questions, it's going to be on these techniques that you've practiced a bunch. Cool beans. Nothing severely catastrophic could really happen. Maybe there's a proof question that you can't do. Maybe you can't remember exactly what integral substitution to use here. For STEP, the questions are just hard. The idea here is that they're testing for your ability to problem solve, your ability to have insight, and also that you know the content so fluidly that you can dedicate all of your cognitive output to interesting new problems. If you have to look at these problems and remember, how do I do that basic thing, or what's that formula, it's going to make everything a lot harder. It's going to make the time especially feel very dense. So we can't afford really that kind of scope. Luckily, STEP is right near the end of our time at high school, so we should be pretty prepared for it in terms of content. Loads of time after university admissions to study for STEP, which is great. Okay, well, let's get into it. I'll let you read the question, give it a shot, and then we'll talk through it. Brilliant. So this question's great. Starts off with a hint. Tells us how to do the problem. Always appreciated. So explain by means of a sketch or otherwise why this thing's the case. Now, whenever they say this, that's basically them being, we probably recommend you do it this way. That's probably the easiest way. If you have some wild lemma that you can apply here that actually solves it, and you could explain to us fully why that's the case, hey, sure, by all means, you can show off your knowledge. But for most people, probably do this. Now, by means of a sketch, what are we going to sketch here? Well, we've got 1 over, and an integral of 1 over. So almost certainly we should sketch here 1 over x squared. So if I just call this x, which of course looks something like this. Let's give n at some point. Let's say, I don't know, let's just say n is here. Cool. So this middle expression is an integral. We know what that looks like. That's this area here. What about the others? So this is 1 over n squared plus 1 over n plus 1 squared plus etc. up to infinity. Now, n squared is this value here. If we move along to n plus 1, it's going to give us that value here, and again n plus 2, n plus 3, etc. How can we represent this on our graph? Well, luckily, n squared is the same, or 1 over n squared is the same as 1 over n squared times 1. So the area on this graph reflected by that n, we can basically draw this rectangle, can't we? Because this rectangle is 1 over n squared vertically and 1 horizontally. So it's got area 1 over n squared. Similarly, 1 over n plus 1 squared is this rectangle here. And then etc. And I think immediately we spot, aha, these rectangles are all above or equal to the curve. So therefore, the infinite area we're going to get by stacking all of these up must be strictly greater than the area of that integral, which explains our inequality here. On the other side here, we've got starting at n plus 1. So that's basically these rectangles onwards, so discounting the first one. Okay, so how can we maneuver that to solve the problem? Well, it's quite nice to keep our contact with the curve here, and actually just shifting all of these one step earlier so that they start below the curve and they move along to hit the curve each time. Again, very nicely and very immediately solves our problem, because all of these rectangles are below or at the curve. Therefore, the brown area we're going to get from adding up all these rectangles, which is equal to this sum here, must be strictly less than the area under the curve. So that's that first part done. Brilliant. They gave us a hint by means of a sketch. We used the hint. We solved the problem. Fantastic. So for part 2, we have some new information or some new inequality we're trying to deduce. Seems to be kind of related to the first one. Maybe these look similar, but it's not exactly clear why. Of course, whenever we're asked to do the next step, the next part of the question almost always relies on the previous part of the question. So we're going to use what we've just done to show what we're about to do. Now, specifically this thing here, which is a little bit awkward. So a is the sum from r equals 1 to infinity of 1 over r squared, and we're subtracting off this thing here. Well, actually, this whole middle thing is just going to be equal to the sum from r equals n plus 1 to infinity, isn't it? Of 1 over r squared. Because we've got all the terms, but then we're ignoring the ones from 1 to n. So what's left will be those from n plus 1 to infinity. Which, hey, that's just this thing over here. Now, immediately we can say, okay, well, we already said this was less than this integral here, and oh, yeah, by the way, of course we can actually solve this integral almost immediately. Now, that integral is going to be equal to infinity n minus 1 over x squared. Voila, that's equal to 1 over n. Fantastic. So this side of things immediately is cleared up for us with that series of observations. Fantastic. Now, of course, this is step. So what I'm not doing here is explaining in words on the paper why this diagram demonstrates my answer. That's mostly because I'm using a mouse and this would take a while. And I'm doing it vocally. I don't want to repeat this information. But know that we need to communicate to the examiner our thoughts, our logical processes. Right? So what I really should be doing is start off by saying, this is larger than this. And then I'd show that this is equal to 1 over n. And then I'd show that this is equal to this thing here. And then I could be like, cool, okay, there's the left-hand side of this big inequality. Done. Now we'll do the right-hand side. So it's almost as if this thing is larger than something that we haven't quite got yet in our inequality. And, well, how can we manipulate this in a way to kind of gain access to this extra piece of the inequality? One observation we can make here is that this statement is true for any value of n. So it's also true for n plus 1. So we may as well just turn all these n's into n plus 1. And actually what this gives us is that part of this inequality is just the integral from n plus 1 to infinity of dx over x squared. Which, dx over x squared, I should say. Which you could probably immediately see is going to be equal to 1 over n plus 1. So there's our second part of this question done. Brilliant. Find the smallest value of n for which this sum approximates a with an error of, okay. Now, if this is approximating a with an error of this, effectively that means the difference between these two is this thing here. So the sum minus a is less than 10 to the minus 4, or a minus the sum is less than 10 to the minus 4. So the sentence certainly has words in it. Actually, very simply, all this means is that n equals, well, 10 to the 4. because we need the difference, i.e. the inaccuracy, i.e. the error in the approximation, is less than 1 in 10,000. N is just 10,000. And then 1 over 10,000 is larger than our error. Now I'll scroll down a little bit here. So we want to show that for this value of n, 10 to the 4, this expression approximates a with an error of less than 10 to the minus 8. Okay, so perhaps rearranging this equation to make a the subject will have things clearer here. So a is going to be larger than our sum term plus 1 over n plus 1, and is going to be less than our sum term plus 1 over n. So the kind of two pieces of bread that are sandwiching our value of a together is this one on the top and this one on the bottom. So the maximum error that this prediction could have of a is simply the gap between our two pieces of bread. The furthest off our lower bound can be from a is if it goes all the way up to the upper bound. So simply these two minus each other, the difference between these two terms. So actually, the error in our approximation is just 1 over n minus 1 over n plus 1, or in this case, that's 1 over 10,000 minus 1 over 10,001. Now, this is not the worst thing in the world to actually evaluate. If we just cross multiply, we get 10,001 minus 10,000 all over 100 million 10,000, and of course 10,001 minus 10,000 is just this, 1.0001 times 10 to the 8. So clearly this is slightly less than 1 part in 10 to the 8. And as long as I explain what I've written here with my words, well, on paper with my words, so the examiner understands the process I've gone through, I think this is a pretty robust solution. Generally, step questions are hard. In a step exam, you may find some questions you can do. I think this question, honestly, fairly friendly. There are much worse step questions out there. This is from step 2, and it's a little bit old as a question, so don't expect it to be particularly accurate in terms of the height of difficulty that step can take. But you as an individual, as a mathematician, will have different strengths and different weaknesses, and it's important that you play to that. You will hopefully be able to find some questions in the test that feel like this, that you can go, okay, here's me running through the question, cool, I think I've got it done. There'll be other questions where it's a brick wall. So the only way we can get a sense of that, obviously, is by doing a whole bunch of step. And the only way you can improve at step questions, I would say, is studying A-level is definitely not enough. The difficulty gap between A-level and step, or equivalent high school exams and step, is just so enormous. You have to be doing step questions, Olympiad questions, right? Even the senior math challenge, I'd say, is far, far off of step. Senior math challenge likes to ask, I think, harder questions on easier maths. This is harder questions on harder maths. So we need to be amply prepared for this in order to stand a chance of surviving. So best of luck.